Hello, welcome to episode 4B. I think I've got this in. There's a kind of a little bit to vector derivatives. It's kind of gone a bit long, but this one's going to be very short. We're just going to be talking about, well, what happens if you take the derivative of vector functions. And I'm only going to be talking about vector functions in one dimension. But we can still totally look at vector functions in multiple dimensions. Really, the main intuition here is you can kind of think of like this R. You can think of this. Let's just think of some position vector R. Okay, so I'm going to draw the graph. X, Y. Right. This is we have some path. Or I'm going to put this in green. R prime. And this is kind of where the physics starts coming in, because I know we've been talking a lot about math, but this is kind of to build up to that intuition about physics. So we have RT. This is a vector function that parameterizes the path of some particle. Okay, so remember, R in this case is a vector from R to Rn, right? N is less than M. So this means that we actually have a space curve, right? Space curve. And so what happens if you take its derivative? Well, what's the derivative of position? Like if we have an object and it's moving here and it's parameterized by this path, what happens if you take its derivative? Well, we're going to get another vector or tangent to that line, right? This is the velocity at that time. Nothing's changed. Nothing's changed from how we originally understand this. And we take that one more time, we're going to get acceleration with respect to time. So what we have is, we have d over dt of r of t. Well, that's just, that's just velocity. And then we have d squared over dt of r of t is equal to d over dt of velocity, which is equal to acceleration. Right, and so there's an interesting shorthand that we're going to be using in physics, where if we have, d over dt of r t, we don't write it like this. We don't even use this r prime, right? We use a dot, so we do r dot t. Right, so we use this guy. And then velocity, well, this is going to be equal to r double dot t. Or velocity is r dot, and acceleration is r double dot. And each dot is, this dot is just equal to d over dt, pretty much. It just tells you that we're taking the derivative twice. And all the rules still apply, but keep in mind that this is a vector. We apply a derivative and we get a vector. We still have to consider things. If we have like momentum is equal to m times v velocity, right? This velocity vector, or actually m times r dot, right? We take the derivative d over dt of this. Well, this is going to be dm over dt r dot plus m r double dot, right? And obviously this is force, that this is acceleration, and then this is going to be 0 for most cases sometimes, right? There isn't too much else to say other than we kind of want to think about what happens if we take actual vector operations, because we have those now. So what happens if you take d over dt of r cross u, you know? Or actually I'm not going to use r, I'm going to use just some x cross r. Okay, what happens? When do you take that? Well, this is a product, right? What I'm saying, derivative of a product? It's the cross product, right? Cross product. We just use the product rule. So that's going to be d over dt of x cross r. And remember, order matters. So we kind of want to keep that. And then we do x cross dr over dt, right? Or another way to think about it, x dot cross r plus x cross r dot, right? That's the better way to write it, right? So we would just get that. And then what happens if we take the dot product, right? D over dt of a dot b, right? And then this here actually is really important when we do angular momentum and angular motion. This is going to come in handy, but we won't talk about that yet. If we take the dot product, well, remember, these are still vectors, but they're still vectors in T. There's no guarantee that just because we take their dot product, we know that this is going to be some scalar value. But what it's actually going to be is it's not going to be some number that we can take that's going to be constant, right? The dot product of two vectors, vector functions, is not going to be just some number. It's actually going to be some function, right? Just think about, okay, a is equal to x squared y, right? And then b is y x squared, right? We take this dot product. These don't cancel out. This is going to give us some function. This is going to give us a dot b is going to give us x squared y squared plus x squared y. That's a function. That's not a number. But you can still take its derivative. So what we're going to be doing is this is also a product. So it's all just a dot b plus, remember, order matters. Well, not so much for the dot product, but then we have a dot db over dt, right? Or in other words, a dot b plus a dot b dot. Okay. And that's pretty much all I want to talk about. I'm not going to talk about the chain rule and other bigger stuff because I'll get into that a little bit later. There is a way to take kind of like the gradient for these things, but it ends up being a matrix, and I'm not going to talk about it right now. But yeah, so thank you for watching. See you in the next one.